Hello class, today we're going to talk about independent samples t-test. Now, the two one-sample t-tests that we've learned are important for understanding the basis of these statistics, but now we're getting to the actual practical test, okay? As I mentioned before, I've never used a one-sample z-test in my actual research. I've used the one-sample t-test maybe once or twice. Independent samples t-test, I do all the time. Paired samples t-test, I do all the time. These are very practical tests. Remember, for these tests, they are independent samples. There's a plural S here. Very infrequently are we going to be dealing with populations in psychology. Okay, that's just the way that things are. Okay, if you're doing a study and you've got people in one condition, okay, people in another condition, you're dealing with sample means. You're dealing with sample standard deviations. You don't got a population. All right, so since we don't have a population, that's going to make our statistics a little bit more different. Okay, it's going to make them a little bit more complicated. But these tests are going to be much more practical. We're going to be seeing these tests very frequently. You're going to do these tests when you're in research methods and when you're in the lab class. I would bet some money on that. Okay, so the independent samples t-test. So we're going to do a couple of things. We're going to talk about the test by itself, run through one example of it, and then I'm going to have some more practice time with you guys so I can run through a couple of examples just so we can make sure that we truly know what's going on here. So we've got ourselves the independent samples t-test. When do we do an independent samples t-test? Well, we're comparing two sample means, okay? We're comparing two sample means. Let me get my little annotate thing out here. But ultimately, we don't care about what these sample means are. So we've got the sample mean here. We've got the sample mean for our second group. But we can see with our eyeballs that these sample means are different from one another. That's not what we care about. We care about inferring what the population mean of these two samples are. We infer what the population means are, and we try to make a comparison. Are these the same thing? Are they different from one another? That's what we are doing. We've got two sample means that we're looking at, and we're trying to infer those sample means in the population. Are those population means similar to one another? Are they different from one another? One's greater than the other one. Okay, so we don't have any population means, none to speak of whatsoever. It's going to make things more difficult for us. You'll see how it's difficult here in a second. Two, we do not have any population variances or population standard deviations. Ooh, this is really problematic for us. Remember that when we were doing all the other tests, okay, we were drawing a sampling distribution of what our data should look like under the null hypothesis. And we know what this sampling distribution looks like because the mean of a sampling distribution is always the population mean. We know that the variation of this sampling distribution is equal to the standard error, so the true population standard deviation over the square root of n. All right, we can draw what this sampling distribution looks like when we have these parameters, but we don't have these parameters now, okay? It's going to make things difficult. How do we know what the data is going to look like under the null hypothesis if we don't have the true population mean and we don't have the true population variance? We're going to have to be a little bit crafty. The other thing that we need when we're doing an independent samples t-test is we have a between subjects manipulation. I have stressed the importance of knowing the difference between a between and a within manipulation. Hopefully that has finally sunk in. For between subjects manipulation, we have subjects either in this group or they're in this group. We measure the dependent variable one time. All right, and so our comparison is going to be between our groups. The comparison is between subjects. These are completely separate groups of people, or another way of saying that is they are independent of one another. Hence the independent samples t-test. Okay. So what do we do for this? Sorry, technical difficulties here. So our job when we are conducting an independent samples t-test is to see if the sample means that we draw from do they come from the same population mean, or do they come from two completely separate populations? That's what the independent samples t-test is all about. Is the population mean for these two samples exactly the same thing? Or is the case that they are different from one another? That's what we're trying to test, okay? We're trying to see if these two independent samples are derived from the same population, okay? So we're going to create a test that does that. So we're going to have two means, okay? Two sample means. We might have mean sub x to indicate the first condition, or maybe mean sub 1 to indicate the first condition, and mean sub 2. And we're trying to see if in the population, if mean 1 and mean 2 come from the same population, or do they come from different populations, okay? So we can express this as follows, okay? The population mean for condition X is it the exact same thing as the population mean for condition Y. Condition X might be the experimental group, condition Y might be the control condition. So we could write the null hypothesis like this, or we could write it like this. If the two means were subtracted from one another, we should see an average of 0. And in fact, this logic right here is what we're going to use, okay, to solve our problem that we don't know what the sampling distribution looks like, okay? We don't know what the mean, the true population mean is, okay, for that sampling distribution. How do we draw it, okay? How do we draw this thing? Well, we're going to rely on a special principle here, all right? If these population means are truly equal to one another, if they're truly equal to one another, okay? And we were to grab two sample means, okay, this one sample mean, this one sample mean, okay, and subtract the two from one another, okay? On average, that difference is going to be 0 if there's truly no difference between the two conditions, okay? So if we were to subtract mean 1 from mean 2, okay, and do this process again and again and again and again and again, so we randomly sample X number of people, we randomly sample Y number of people, we calculate those means, we take the difference, we subtract them from one another, and we write that down in our ledger, and we do that dance again and again and again. Very similar to a sampling distribution, but now we're doing a special sampling distribution. It's called a sampling distribution of the difference between two means, okay? Sampling distribution of the difference between two means. We know that under the null hypothesis that the average should be 0, okay? If there's truly no difference between these two, if we do this dance again and again and again, sometimes condition 1 will be greater than condition 2. Sometimes condition 2 will be greater than condition 1. But in the long haul, over a long number of iterations, okay, we're going to get a sampling distribution, and the mean is going to be 0. On average, okay, we're going to get 0 differences if we were to subtract mean 1 from mean 2. That's the logic that we're going to use to solve our problem here of not being able to draw our sampling distribution. Okay. Okay, so here's the problem that we are going to do. So we have a sample of 40 female Georgia Tech students and a sample of 40 male Georgia Tech students, and we're going to assess their satisfaction with academic advising at Georgia Tech. And they're going to use a 10-point Likert scale, where 1 is very dissatisfied, I hate my advising, and 10 is very satisfied, okay? There are 2 violations of some of the assumptions of parametric tests with this example. And that's one of the reasons that I select this example, okay? So 2 things that I want you to pay attention to with this problem. Now we can do the independent samples t-test, but we need to be careful about our conclusions. Problem number 1, all right? We're not manipulating the independent variable. This is not a true experiment, all right? So we're not going to make a causal attribute that being female or being male actually causes a difference. There might be some other things that lead to this causal relationship. So we're truly not manipulating the independent variable. And you should be thinking that when you uncover a problem like this, or when you think about a problem like this, okay? But this is a between subjects manipulation, okay, or between subjects variable, okay? You're either in the female condition or you're in the male condition. So we can use the statistic. We just need to be cautious about our interpretation, especially of causality here. Right. The other thing is that we have a Likert type scale. Likert type scale is an ordinal scale of measurement. Remember when we talked about that? And since it's ordinal, we need to be cautious about the interpretation as well. I just wanted to remind you guys of those things, that there's things that you're supposed to be thinking about. But we can still use this statistic for this problem. We just need to be cautious about our interpretations. Also, it's time for you guys to start thinking about advising. So make sure that you have scheduled an advising appointment with your advisors, specifically within psychology. That would be very, very useful. Let me tell you a little bit about Georgia Tech advising. You guys have your own advisor. You can meet with the advisor. They help you with classes, all that sort of thing. Not at Georgia Tech. At Georgia Tech, all the psychology majors have one advisor. And there are 2 periods in the evening where you can come to a classroom with like 50 other people, and the advisor gives a lecture about what you need to be doing in the psychology major. And he might answer some questions, but there's no one-on-one advising. Okay, so feel very fortunate that that's not what you guys have, that you have an advisor that can help you personally answer questions. So also make sure that you take advantage of that as well. Okay, so in the population of Georgia Tech students, are there gender differences, or in this case, since I use male and female, we call them sex differences in satisfaction scores with academic advising? All right, differences. Oh, that lets you know something. Differences are things different. I'm referring to a two-tailed test. All right, so let's talk about qualities of this study. We have the sex of individuals, either male or female. Okay, the dependent variable are the satisfaction ratings. It's a two-tailed test. That's what I know when I look at this study. Okay, so how would I write these hypotheses? I could do this one of 2 ways. I could say the population mean of females minus the population mean of males is equal to 0. I could say, or I could say the population mean of females is equal to the population mean of males. Typically, I am going to use this one when I draw it out myself, but it doesn't matter. Both of them are equally valid, equally good. Which one of the population means do you put first? Do we say that females are the first group? Do we say that males are the first group? It doesn't really matter, especially if we have a two-tailed test. But eventually, you are going to take a difference of the means. So you're going to take mean 1, which might be males or females, and subtract it from the second mean. So this means that your t-value is going to be negative or positive depending on which group you put first. For a two-tailed test, this doesn't matter. If your t-value is negative, is it positive? Doesn't matter as long as it's significant. But you will be tripped up when you start doing a one-tailed test. With a one-tailed test, the t needs to be a certain direction. Okay, so be mindful of that when we start doing one-tailed tests with independent samples t-test. It doesn't matter which group you call mean 1 and mean 2, but you need to be consistent throughout your problem, or else you might make a mistake. Okay. Okay, that's the null hypothesis. The alternative hypothesis is the population mean for females does not equal the population mean for males, or the population mean of females minus the population mean of males does not equal 0. Okay. So here is our scenario. Okay, so we're going to sample 40 female Georgia Tech students and 40 male Georgia Tech students, and we're going to give them the satisfaction scale. All right, so we're going to compute the sample mean for females. We're going to compute the sample mean for males. And then what we're going to do is we're going to subtract them from one another. Okay, and we're going to write that difference between the two means in our ledger. in our notebook. And then we're going to do this process again. We're going to randomly select another 40 males. We're going to randomly select another 40 females, take the difference, write it in our notebook, and we're going to do this process again and again and again. Okay? So we write the differences between the two means on a sheet of paper. We replace the sample back into the population of Georgia Tech students, and we do this again and again and again. And so we do this millions and millions of times, thousands of times. Okay, we don't actually do this, but we're just talking about theoretically right now. And this is going to give us a special sampling distribution. We're going to call it the sampling distribution of the difference between two means. Okay, technically the sampling distribution of the difference between two independent means, but you know, I like to say it a little bit quicker if I can do that. So independence not necessarily necessary in this particular case. And what this is going to do is it's going to show us, it's going to tell us specifically what this sampling distribution is going to look like. We know that the mean is going to be 0. Now we do need to find out what the standard deviation of this sampling distribution is going to be. Okay, we need that to be able to find out if the statistic is significantly different. So the standard deviation of a sampling distribution is, of course, the standard error. But the standard deviation of this particular sampling distribution, the sampling distribution of the difference between two means, we're going to write that out as little s underscore difference. Okay, that's how you'll see this in my notes. We need to calculate this so that we can do our statistic. Okay, so when we end up calculating the t-statistic, it's going to be the mean of group 1 minus the mean of group 2. And hey, one mean minus another mean. That's how we've done every single inferential statistic so far. And then we divide that by the standard deviation of our sampling distribution. Okay? In many instances, this is the standard error of the mean. So we do something like this. But not now. Now we're going to put S difference here in the denominator. What is S difference? It's the standard deviation of the sampling distribution of the difference between two means. How do we calculate this? Well, you'll just have to wait a little bit and everything will become apparent, hopefully. Okay. So we might see something similar to this if we were to do this, let's say 30 times and not 1,000 times or 1,000,000 times, okay? The average difference between the two, if there's truly no difference, if the null hypothesis is true, they are likely to be centered around 0. Okay, sometimes mean 1 is going to be greater than mean 2, sometimes mean 2 is going to be greater than mean 1, but they should be centered around 0 if the null hypothesis is true. Okay, so the sampling distribution of the difference between two independent means will form a normal distribution. Okay, whenever the two means on which it is based come from sampling distributions which are normal, okay, that are normal distributed. Okay, so if we have a sample size of 30 or more, we know that these sampling distributions are going to be normally distributed due to the central limit theorem. Okay, central limit theorem is very important for statistics. Okay, where do we hop into the problem? Okay, so how do we end up finding out what is the true, how do we find out what S difference is, the standard deviation of that sampling distribution of the difference between two means? Well, when we didn't have the population variance, we had to estimate what it was. When we didn't have the population variance, we used the sample variance. Okay, we used the sample variance and inferred that this was similar enough to what the true population variance is. Remember, one of the assumptions of parametric test is homogeny of variances, that this and this should be relatively equal to one another. In the population, this population variance should be the same as the population variance that we have already found for a one sample z-test at least. Okay. But now, instead of having one sample variance, we have two sample variances. We have the sample variance for group 1, and we have the sample variance for group 2. In our problem, we have the sample variance for men, and we have the sample variance for females. Which one of those should we use? Okay, should we use the first one? Should we use the second one? Well, if you think about it, well, it's probably some combination of the both of these. That would be the best predictor of what the true population variance is. Under the homogeny of variance assumption, the population variance of females and population variance of males is equal to one another. So if we can combine these in some way, that's going to give us the most accurate prediction of what the true population variance is. So what we're going to do is we're going to pool our variances. We're going to pool our variance estimates. How are we going to do that? Okay, so there is the long version that's always going to work, and then there's the short version that is going to work in some specific instances. The long version is this. We're going to take the variance of group 1, it's the variance of our group X here, and our variance of group 2. And we're going to multiply both of these variances, okay, by this expression, the degrees of freedom for the first group over the total degrees of freedom. And for the second group, we're going to multiply it by the degrees of freedom for the second group all over the degrees of freedom of total. And then we add these two expressions together, and that's going to give us the pooled variance. What this does is it's going to weight more heavily the group that we have more subjects in. If we have, let's say, 60 male subjects and 30 female subjects, well, the male subjects, the male variance is probably a more accurate estimate than the female variance, okay, just because there's more subjects there. So we are going to weight them by their degrees of freedom, and the degrees of freedom are related to how many subjects are in each group. But if there is a special circumstance in which we have the same number of subjects in both conditions, okay, same number of subjects that are in the male condition, same number of subjects that are there in the female condition, this expression simplifies to something even easier, okay? The variance pooled is equal to the two variances added together, all divided by 2, okay? So you just take the average of the variances if we have the same number of subjects in both groups, and that is our pooled variance. That is the best estimate that we can have of what the true population variance is if we have an independent samples t-test. Okay, but we're not done, unfortunately. We've got the pooled variance. We kind of have an estimate of what the population variance would be for these two conditions. But how about the standard deviation of that sampling distribution of the difference between two means? Okay. Many times we have gotten, okay, the variance, but we always have to do something to it. We have to weight it in some regard due to the number of subjects that we have, okay? So sometimes, for instance, we have the population standard deviation and we divide it by the square root of n, okay? This is our standard error. So what's our standard error going to be like for our sampling distribution of the difference between two means? Well, we're going to take ye old pooled variance, and we're going to multiply it by 1 over the n sub 1 plus 1 over n sub 2. This is the number of subjects in group 1 and the number of subjects in group 2. Okay, when I use little n from now on, I'm referring to the number of subjects in a particular condition. Okay, the number of subjects for the males, maybe, and the number of subjects for the females. That's what I mean when I do this. Okay, so for instance, if we've got our pooled variance, I would then multiply the pooled variance. Well, we've got 40 subjects in both conditions, so that'd be 1 over 4, 1 over 40, plus 1 over 40. So that's going to give me 2/40ths or 1/20th, and we multiply that by the pooled variance. This is very similar to having a population variance and then doing something to it so it is the standard error of the mean. Okay, so we do that, but again, we're not exactly done. Okay, we've got S squared difference. Okay, and if we want to get S difference, which we're going to use in our denominator, which is the bottom part of the fraction, for our t-test, what we need to do is we need to take the square root of S squared difference. Okay, so we take this expression and we take the square root of it. My handwriting is lovely. I was talking with Chuck today, and Chuck was like, hey, wouldn't it be better if you had an iPad and had a stylus? And I was like, yeah, that'd be great. Do you want to buy one for me? And he was like, well, yeah, you have a point. But yeah, maybe one day I'll get a stylus and these drawings will be a whole lot better. But my handwriting's not that much better, so I don't know how much that's truly going to help. Okay, so we need to find S difference. Okay, so let's return to our example of gender differences and student satisfaction with their academic advising. Okay, so the number of subjects that we have is 40 in both conditions. Okay, we're going to do the 4 steps. We want to make sure that our alpha is 0.50, so there's only a 5% chance that we reject the null hypothesis, and the null hypothesis is actually true. Okay, let me scooch forward a little bit here. So we need to figure out what our degrees of freedom are. Okay, and our degrees of freedom are going to be big N minus 2. And the reason for this is we have 2 sample means. We've got sample mean number 1, we've got sample mean number 2. All right, and let's say that we have 3 subjects in both conditions. Now, is this degree of freedom, is this instance able to vary? Yes. This instance able to vary? Yes. But for this mean to be what it is, particularly this last one can't vary. Same thing for the second mean. These 2 can vary, this last one cannot. So our degrees of freedom for an independent samples t-test is big N, which is the total number of subjects in the entire experiment, minus 2. It's a little bit different from the degrees of freedom for a 1 sample t-test. There it is N minus 1. Okay. Also, since we are approximating what the true population difference is, and we don't actually know, we have to use the t-distributions as opposed to the standard normal distribution. But you kind of figure that out because we call it a t-test and we don't call it a z-test. Okay. So our t statistic is going to be the 2 means subtracted from one another, and we're going to have S difference in the denominator. Okay, and I've already showed you how to calculate S difference. And we're going to look up the cutoff value in our table, okay, by looking at that t distribution. Okay, so let's finally get to this problem and work it out for you guys. 1 second. All right, so let's solve our first example of an independent samples t-test. So we've got the mean for females, the mean for males, the variance for females, the variance for males, and the number of subjects for females and the number of subjects for males. Okay, so let's go about solving this problem. So our big N is 80. We've got our variances here. We know it's a 2-tailed test. Let's go through the 4 steps. Okay, so first thing first, let's write our step 1. So the best way to write this is probably, this is just the simplest way. Okay, population mean for females is equal to the population mean of males because we have a 2-tailed test. And of course, the alternative is just going to be does not equal. These 2 population means don't equal one another. For step 2, alpha is equal to 0.05. We've got an independent samples t-test, as we've already mentioned before. If we care about just the difference, not the direction of the difference, we have a two-tailed test. All right, so to calculate our degrees of freedom, okay, we need the total, the big N, which is 80, minus 2, which is going to give us 78. Okay, there's no 78 in our table. And when that happens, we want to go to the value with the lower degrees of freedom. Okay, so there should be a value for 80 probably, and a value for 60. Let's go for the 61. So T critical is going to be above 2.0 and lower than, so our T critical is plus or minus 2.0. But we reject the null if we have a T value greater than 2, and we have a T value that's less than negative 2. In both of those situations, we reject the null hypothesis. Okay, let's do step 3. This is a lot of information right here. Let's pay attention to the particular formula here. So we take our two means, we subtract them from one another, and then we put in the denominator S difference. Okay, so let's calculate S difference first. The first thing that we're going to do is we're going to pool our variance. Okay, to pool our variance, I did it the long way here. Oops. We could do it a quicker way. Okay, we have that the variance of the first group is 1.20. The variance of the second group is 1.25. Since there's the same number of subjects in both of these conditions, we can just divide that by 2. It's going to leave us with a pooled variance of 1.225. All right, so we've got our pooled variance. Now what we need to do is to find S difference. We're going to take that value of 1.225 and we're going to multiply it by 1 over the n of group 1 plus 1 over n of group 2. And when we solve that, we're going to take the square root of that to get S difference. So T, okay, is going to be equal to the two means minus one another. So 8.8 minus 8.1 all over S difference, which we solved, is going to be 0.2475. And when we do this, we find a T value of 2.828. This is greater than positive 2.00, so we're going to reject the null hypothesis. Okay, so we are rejecting the null hypothesis, but we're not done with our step 3. We always want to make sure that we include an effect size, so let's put Cohen's d. Cohen's d, same formula as it's always been, but this time instead of taking the sample mean minus the population mean, we just have mean 1 minus mean 2, and we take as the denominator, instead of just a standard deviation, it's going to be the pooled standard deviation. So we take the pooled variance, we take the square root of that. So if we do that, we get 8.8 minus 8.1 all over 1.1068. That's the square root of 1.225. It's going to give us a Cohen's d of 0.632. And this is the Cohen's d that we're going to report. Now, Cohen's d is directional, but many times in articles, you'll see that the Cohen's d is just always positive. Okay, the reason for this is it's completely arbitrary which group you call group 1 and which group you call group 2. And whatever you put Cohen's d as, you can look at the mean difference and tell which group scored higher and which group scored lower. All right, so if you always give me a positive Cohen's d, that's perfectly fine. If you give the Cohen's d with however this math works out as to what group you call group 1 and what group you call group 2, that's perfectly fine as well. Okay, so let's write up the step 4. So we reject the null hypothesis in favor of the alternative that the population of GT students, okay, females, mean equals 0.8 or mean equals 8.8, have a different satisfaction score with academic advising than males, mean equals 8.1. For our T statistic, we're going to have T with the degrees of freedom here, which is 78, equals 2.828. P is less than 0.05 because we're rejecting the hypothesis, and then we're going to report what Cohen's d is. Okay, so we went through the logic, we went through an example. In the next video, we'll go through a couple more examples. Okay, thank you guys, and have a great day. Bye-bye.